Well, good day. My name is David Bourell. I'm the state director for the Calculator Applications Contest with the UIL. And it's a pleasure to be here today to visit with you and to talk about a certain type of problem that appears on the Calculator Applications Contest. So without any further ado, let me share my screen and let's see where we are here. So here we go. Let's move this up a little bit. What I want to talk to you today for this time period, this slot is acceleration problems. And there's also a subclass of acceleration problems or trajectory problems. So I'll talk about those as well. So let's just jump right in. These problems can occur anywhere on the contest. Although for the last few years, problem number 63 has been a trajectory problem. So if you look at the last 2 or 3 years of contest, problem 63 is guaranteed to be a trajectory problem. And my plan for 2022 content, the 2022 contest year, is for problem 63 to be a trajectory problem. So you can be guaranteed you'll see one of these problems on the test, at least one in problem 63. And as you might guess, these are relatively complicated problems, so they don't appear early in the test. They appear in the locations where I put typically the harder problems, and that's typically the page 4 problems, stated problems, 36, 37, and 38. Problem 60, well, it could be problem 61, but typically is not, because 63 is a trajectory problem. And so anyway, they're typically the harder problems on the test is where we see these. In terms of acceleration, the reason that I put acceleration and trajectory problems on the test is I view the Calculator Applications Contest as being kind of a pre-engineering contest. And in engineering, we sort of look at the world around us and apply mathematical and science principles in order to accomplish something typically. And so certainly, if you look at the world around you, it's replete with examples of acceleration, deceleration, and trajectories. So just as you see here, all kinds of objects of the world move: footballs, gears, bikes, people, satellites, bullets, planets, cars, and on and on. And if an object changes speed, if it slows down or speeds up, for example, a car slowing down as it enters a school zone or as it approaches a red light, then it's accelerating or decelerating. Of course, deceleration is simply a negative acceleration. But it could be a change in direction. If I have a ship that's traveling at 30 miles an hour north and it changes direction by 10 degrees to travel, say, a little bit to the east or a little bit to the west of north, even if it stays at 30 miles an hour, it's still accelerating or decelerating because it's taking on a change of direction, which involves an increase in this case, we might think of it as an easterly or westerly velocity change. And if the velocity changes over time, then it's an acceleration. So whether it speeds up, slows down, or slows down, or changes direction, we have an acceleration. Now, the one way that you might think about acceleration is, say, a plot that looks like this. If I have an object traveling along, in this case, looking at the plot at 30 miles an hour, and at 10 seconds on my stopwatch, I start my stopwatch. After 10 seconds, I could change the velocity of that object. I could up the speed to 35 miles an hour. What we could do is, you might consider the easiest thing to do would be to show this, where we simply instantaneously change the object's velocity from 30 to 35 miles an hour. Well, the problem is, I show the mathematical formulation for this, where tau would be the point at which the velocity changes instantaneously. In this case, 10 seconds. V naught here would be 30 miles an hour, and VF would be 35 miles an hour. So we have that going. The problem with this is that virtually no object accelerates instantaneously like this, or instantaneously changes velocity. The problem is, I guess we could blame, to some degree, we could blame Mother Nature. If you look at, consider Newton's law, his first law, says that the force required to change, to accelerate an object is equal to the mass of the object times the acceleration. So we have the famous equation F equals ma, force equals mass times acceleration. Well, if I accelerated a really high acceleration, which in this case, what I show you here is the acceleration is infinite from as I jump from 30 to 35 miles an hour, or it's an incredibly high number. Effectively, on a velocity time plot like this, the slope of the line would give the value of the acceleration. So for example, on the left side and the right side, where I'm going at 30 or 35 miles an hour, the slope is zero, so there's zero acceleration. On the vertical jump from 30 to 35, it's infinite or extremely high, as the case may be. Well, here's where the problem is if let's say this is a car driving, a car weighs a couple of thousand pounds. That's got quite a large mass. Well, the deal is it takes an enormous amount of force to accelerate that car at a very high acceleration, right? Because F equals ma. If my a approaches infinity, my force approaches infinity. And the deal is that just doesn't happen in Mother Nature. So what we do is we rather have a velocity curve versus time that would look maybe more like one of these two plots, where we have now a finite acceleration that takes place, and the acceleration doesn't become infinite anywhere. So what we see are these two plots. I would say the one on the right, which is sort of sigmoidal, I'll get to it in a second. It's perhaps the more accurate of what you would really see in the real world. The left one shows a point-wise change in the velocity associated with the change in the acceleration. But it turns out the one on the left is the one that we use more often than not in the calculator contest. And again, it has problems, but not nearly the problems that we would have assuming infinite acceleration. So anyway, so looking at the left, what we have is we travel along at 30 miles an hour with zero acceleration. And then at 10 miles, at time mark 10 seconds, we instantaneously change the acceleration, not to infinity, but rather we change it instantaneously to some finite value. And the value of that I can get is the slope of that slant line, which I guess we can calculate that slope easily enough, because it looks like the vertical rise is 5 miles an hour, and the horizontal run looks like 15 seconds. So it's going to be 5 over 15 miles per hour per second, or 1 mile per hour per 3 seconds would be the acceleration. And that changes instantaneously from zero to that value. And then, of course, at the end, once we hit 35 miles an hour, we instantaneously change the acceleration from that value of 1 mile per hour per 3 seconds to back to zero. And again, that change happens instantaneously. So, and we go back to zero acceleration once we hit 35 miles an hour. Well, this also is the reason that we don't really like this is the acceleration doesn't like to jump to infinity. The acceleration doesn't like to change instantaneously, even from between two finite numbers either. And some of you may be familiar. If this makes sense, this is great. Otherwise, ignore it. But we can think of distance traveled. Our velocity is the time rate of change of distance. Acceleration is the time rate of change of velocity. And it turns out there's also a term that's the time rate of change of acceleration, and that's called the jerk. And we typically don't like high values of jerk either. And in this case, when I instantaneously change the acceleration, I get an infinite jerk, which is really high, and that also doesn't really occur in the real world. So for that reason, this right plot, it shows a more gently changing acceleration as we go from 10 seconds forward through till about maybe 18 or 19 seconds. Then I gently start decreasing the acceleration. That really is more like what we see in the real world if we were actually doing measurements. Having said that, doing sigmoidal type plots like this, where in this case I would, instead of writing the equation for a line, I would use a sine or cosine function to describe the velocity. And I also would use the sine or cosine function to describe the acceleration, because again, the acceleration is the time derivative of velocity. So if velocity has a sine or cosine form, then the acceleration will too, by taking the derivatives. So anyways, even though that's perhaps more correct, it's harder to deal with. And then so we, on the contest, I use the again, almost always the a linear acceleration that changes instantaneously. So basically the left plot is the form that we use when dealing with acceleration and trajectory type problems. Okay, so again, so the acceleration is linear. We can write an equation for the velocity of this general form. This is one of the sort of two equations for acceleration that we use. It's the form of the velocity. The velocity is equal to v naught plus the acceleration times t minus tau. And you can see the terms here in the plot. The acceleration is the slope of the line during the acceleration. Tau is the time mark where we start the acceleration, and v naught is the initial velocity when we start the acceleration. And so what this does is this equation gives me an equation for the non-zero sloped line on the plot. So basically it describes the velocity from time equal to 10 seconds to time equal to 25 seconds, right? And indeed, if the slope is positive, that is, if a is a positive number, then we're accelerating. The velocity is increasing with time as time goes on. But if the acceleration is negative, then the velocity decreases with time. So we would, typically we would refer to that as a deceleration or a negative acceleration. But basically it's the same term. We don't have a different variable for deceleration. We just simply have a negative acceleration. Okay, so for the graph, you can see here, again, v naught's 30 miles an hour, tau is 10 seconds, and my acceleration, as you see, right, as I mentioned earlier, is a third of a mile per hour per second. So I could write the equation as the velocity is 30 miles an hour times 10 minus 10, t minus 10 seconds, mile per hour over 3 seconds. So that would give me the equation that would describe the velocity as a function of time during an acceleration. Okay, so we can come up with a degenerate form of this more general equation if we assume that the velocity, the initial velocity, is zero, in which, in some cases you can, some cases you can't. But oftentimes we have objects that start from rest. That is, they're not moving when the acceleration starts. In that case, v naught is zero. And if I set my time clock, my stopwatch, such that 0 seconds, when I start my stopwatch, it's right at the beginning of the acceleration, then my tau is 0 too. So if v naught and tau are both 0, you can see that this more general form of the velocity equation can degenerate down to simply acceleration times time, which is sort of the equivalent to our old friend in the rate equations of distance is velocity times time. Again, that assumes that this distance equals velocity times time, that old more familiar equation, assumes that my d naught, that my tape measure, I set to 0 when I start measuring the distance, or when the velocity becomes positive at d naught or at v. So at any rate, this is the same kind of equation in this case, because we're one step higher in the integral. We have two constants of proportionality, whereas in the distance equation, there's only one constant, d naught. In the velocity equation, there's two constants of proportionality.
Sorry, I didn't catch that. Try tapping above to edit.
Okay. So the anyway, well, I'm not sure what that was, but anyway, but with velocity, we have two constants of integration, v naught and tau. So anyway, so here's where we are. So we have, I guess that's not really true. I guess it's a d naught and v naught. But anyway, again, the acceleration goes down if it's negative. So here we are, the acceleration. Here's an example problem. This was a problem in test G from 2016, which may have been the second regional test. I think probably back then that's the second district test, I mean. So here we go. Every Formula One racing car can decelerate from 110 miles an hour to 0 and then accelerate back to 110 miles an hour, all in less than 6 seconds. Assuming deceleration and acceleration are equal, what minimum positive acceleration does this represent? And I want the answer in feet per second squared. So we can work this problem. I would imagine in my head a plot like this if I were working it. I start at 110 miles an hour on my velocity time plot. I decelerate to 0 in 3 seconds, and then I accelerate back up to 110 miles an hour linearly in 3 more seconds to give me a total of 6 seconds. So the minimum positive acceleration would take the full 6 seconds. And so I can get the acceleration in a fairly straightforward manner then, because if I look at the right side of the acceleration from 3 to 6 seconds, I simply calculate the slope. I have 110 miles an hour of velocity, and the time is 3 seconds. That's the interval of the acceleration. So I can solve this for A. The acceleration is 110 miles over 3 second hour, or 110 miles per hour over 3 seconds. And then I use 2 unit conversions. So here I have the squiggly brackets are representing unit conversions, where basically inside the squiggly bracket is 1, just a dimensionless 1. But I write it in the form, in this case, 5,280 feet on top is equal to 1 mile. So if they're equal, then when I write the fraction like this, I'm multiplying by 1. The same thing's true for an hour and 3,600 seconds. So I could do that. I cancel out the hours, which are 1 in the numerator, 1 in the denominator. I cancel out the miles, 1 in the numerator, 1 in the denominator. And what I wind up with then is feet per second squared. And the answer is 53.8, 50 feet per second squared. Okay, we talked about the velocity as a function of time during an acceleration. Let's talk about the distance traveled as a function of time during an acceleration. So how does the distance change of the traveling object during an acceleration? Obviously, when we're moving at constant velocity, the distance increases linearly, right, as we move away from some initial point. But when we accelerate, the velocity is increasing, so the rate of my accumulation of distance increases. So I'm going to have a change in slope on my distance plot. So so in this case, there's sort of a good news and bad news. The good news is it's relatively easy and straightforward to derive the distance equation. The bad news is I need to use calculus to do it. So I'm going to do it that way. So if you're not familiar with the calculus or it doesn't make sense, then just ignore it and wait for the final answer. So what I can do is the velocity is equal to the integral of the acceleration times the differential time. So it's the integral of ADT. And when I integrate that out, I get AT plus a constant of integration, which would be my V naught term. But then what I could do is my velocity, by the distance traveled, is equal to the velocity, the integral of velocity times over time. So it'd be an integral of VDT. So I can substitute my V naught plus AT from the velocity equation into that equation. And when I integrate it out, what I wind up with, so I wind up with a D naught, which is the second constant of integration, plus V naught integrates to V naught T, and then my AT integrates to 1/2 AT squared. So I have this equation then, that's the general equation for the distance that's traveled during an acceleration. And we can see that it's parabolic, so it's in the ever increasing slope. So we can see that, for example, in this case, I have an acceleration of 5 feet per second squared. We start with its 0 velocity, and the orange straight line is the velocity, which we read off the left vertical axis. And you can see that we're accelerating linearly at 5 feet per second. So every second, I accelerate by 5 feet per second. So after 5 seconds, you can see I'm at 5 seconds times 5 feet per second squared gives me 25 feet per second would be my velocity, which is what you see here. So it's linear, but the distance is the blue line that uses the right vertical axis. Notice in this case that we actually have the parabolic form for this, and it sort of makes sense because the way I think of it is that at small times, early in the acceleration, I have a small velocity. So let's say in a 1 second time interval, I would travel a distance, a small distance. Whereas when the velocity increases, say up here at 20, 25 seconds, where the velocity is much higher over that same 1 second interval, I'm going to cover a lot more distance because I'm moving faster. So the slope would increase on the distance plot, and that's exactly what we see here. So for constant accelerations, the velocity increases linearly, the distance increases parabolically. Okay, so here's an example. Okay, a car travels from rest at 25 feet per second squared. What's the car's velocity after it's traveled 150 feet? So this case, I know the distance, and I need to solve for the velocity after 150 feet. So the way I do this is I start with the distance equation. I wrote the general form of the equation, but since it's accelerating from rest, v naught is 0, and I set my tape measure so that the acceleration starts at a distance equal to 0. So that's where I lay my tape measure, starting at the start of the acceleration. And so that would be the 150 feet would be comparable then. And so what I do is I substitute in 0 2 places in the distance equation. So the only term that's left is my 1/2 times the acceleration, 25 feet per second squared, times time squared. So the 1/2 AT squared is the only non-zero term. So I have my 12.5 feet per second squared t squared, and I set that equal to 150 feet. And I solve for the time, so I can calculate how long it takes to get for it to travel 150 feet, and you can see that solved out to be 3.46 seconds. Once I have the time, I can substitute that into my velocity equation. V naught is still equal to 0 because I'm starting from rest. And so I have 25 feet per second squared times my 3.46 seconds gives me 86.6 feet per second. I need to convert that to miles per hour, so I use the unit conversions as I did earlier. And you can see those, and that multiplies out to about 59.0 miles per hour. So I'm going about 60 miles an hour after 150 feet. Well, it's not surprising that I could play around. I could play around with these equations. I could write the velocity as a function of the distance, in which case I don't have to solve for the time. I could just simply plug in 150 feet and see what the velocity is. And that's relatively easy to do because in this case, the distance is simply AT squared and the velocity is AT. So I can solve the distance equation for A and substitute that into the velocity equation and see what I get. All right, so let's talk about the Earth and gravity, because gravity also, any object in a gravitational field accelerates. And so on Earth, we have gravity. It causes objects to accelerate to the ground. So if I take an object and I hold it up here and I let it go, obviously we all know what will happen. It'll fall to the ground. Well, it doesn't just fall to the ground. It actually accelerates to the ground. So it's accelerating at a constant rate. And that rate, that specific acceleration, we call it typically in engineering, I suppose in science as well, we call that term G to indicate that it's it's an acceleration due to gravity. And by contest rules on Earth, we define that gravitational acceleration G to be negative 32.174 feet per second squared. So what we have then is that's constant. It doesn't matter what how much the object weighs that I'm dropping. A heavy object doesn't drop any faster than a light object. That was proven, I guess, or demonstrated by Galileo at the Leaning Tower of Pisa, right, where he dropped the two objects of highly disparate mass, and they both hit the ground at the same time. There's actually a fairly spectacular experiment. Maybe if you go look on YouTube with the right search, you can find it. But people have done experiments in these large vacuum chambers that are where they reduce the air, they pull the air out to a very low air pressure, and they'll drop a feather and a lead weight for over a fairly large distance, 10 or 20 feet in this humongous big vacuum chamber. And indeed, the feather and the lead weight drop at the same rates, or with the same velocities, and hit the floor at the same time because they're accelerating at the same rate. The reason that doesn't work in real life, if I held a feather out and a stone in the room that I'm sitting in, the feather obviously would drop slower. The reason why is because the air actually poses a reasonable amount of resistance to the motion of the feather since it's such a light mass. The air also imposes a force on the stone, but since the stone is so massive that that effect is very small or negligible. Okay, so yes, that's where we are. Let me say something about the negative sign. You know, the negative sign is associated with the convention, this negative sign on G, the acceleration, that we typically measure distance from the ground up as positive. So for example, if I'm measuring something from the ground, I typically put my tape measure, I start my tape measure at the ground and then I measure upwards, 2, 3 feet, 3 feet, 4 feet, 5 feet as I go upwards. And that's the positive distance. So my distance axis is positive pointing upwards away from the earth or away from the ground. Well, because the gravitational force causes objects to move downward to decreasing distances to zero at the ground eventually, it's actually a deceleration technically. So it's really a deceleration of gravity, you might think, but nobody calls it that. We call it acceleration due to gravity. But at any rate, to make problems work out so that my distance is positive upward, which is a standard convention in science and engineering, we have to have the acceleration be negative or a deceleration. The only thing I guess I'd like to mention about gravity is that if you look at the physics of gravitational forces, any two masses that are in contact, that are in proximity of each other, will experience a gravitational field. As a matter of fact, I remember some time ago calculating the force of the quote force of attraction between a boyfriend and girlfriend who were maybe 3 or 4 feet apart and who each had a certain weight. And you can calculate that, and it's a non-zero force. Of course, it's infinitesimally small. But when you have an object that's fairly massive like the Earth underneath us, you can get a reasonable gravitational force, and that's where the acceleration due to gravity comes from. Again, because the force is related to the acceleration by the mass by Newton's first law, F equals ma. So clearly, if I go somewhere else, if I go to the moon or I go to Mars or Pluto, then the same rules apply in terms of acceleration, velocity, and distance traveled. It's just that I have a different gravitational constant, they call it, which is the acceleration due to gravity associated with those planets which have different masses from the Earth. So clearly, if the planet has less mass, I would have a smaller acceleration due to gravity. So on the moon and on Pluto, which are smaller, those accelerations would be a smaller absolute number than 32.174. If we go to a planet that's much more massive like Jupiter, then I'd have a higher gravitational constant, higher than 32.174, at least a larger algebraic value. Okay, let's move on. This shows, just for the example, if I took an object, this is for an object that I'm going to let free fall. I'm going to hold it up at a distance 100 feet above the ground, which say be maybe on a 7 or 8 story building. I go to the edge, I hold my my object over the edge, and I just let it free fall. I let it go, and it drops. Well, it'll accelerate. Again, in this case, my V naught is 0 because I'm not throwing it down or throwing it up. I'm just letting it go and letting it fall. So its initial velocity is 0. And I could calculate then using the distance and velocity equations. The distance and velocity is a function of time, which is shown on the plot. Again, the orange plot is the velocity on the left side. The blue is the distance traveled on the right side. We see that due to the acceleration, the velocity is changing linearly. That's the orange curve. And the blue curve is changing parabolically, as we see here in this case. Furthermore, if we've traveled out to where I hit the ground, which is at d equals 0, that's at 2.5 seconds, according to this plot. And I can also see there that at 2.5 seconds, my acceleration is negative 80 feet per second. Again, a negative velocity means simply I'm moving downwards with some speed. So I'm accelerating towards basically at the point of impact with the ground. This object was moving at 80 feet per second towards the ground, which is negative. 80 feet per second, again, for the last problem, that's about 50 miles an hour. So it's pretty good, pretty hefty velocity. Okay. So here's the another example. This is sort of a backwards example from the previous one. This was from 2018 on test E. Notice it's problem 63, which is a pretty high number. Again, we don't typically see these early in the test. They're typically late in the test. And again, this was problem 63, which is where I stick by convention, stick the acceleration problems. So here we go. Larry tossed a ball off the Burj Khalifa building in Dubai, the tallest building in the world. The ball had a release angle of 35 plus 35 degrees relative to the horizontal. So basically, Larry's sort of throwing it upwards and away from the building, which is what I would do if I was on top of the tallest building in the world. I wouldn't want to be leaning over the edge to drop it. I'd stand back far away from the edge and I'd chunk it with some velocity off the edge, right? With some positive velocity, which means it goes, as at least my hand, it starts traveling up in the air. So, this is a new twist on the problem, 35-degree relative velocity. How do we handle that in the problem solving? I'll show you that in the solution. And it's got a release velocity of 45 feet per second. Okay, so it hits the ground in 13.8 seconds. And the question is, how tall is the building? So it's sort of a backward solution. In the first one, I knew the height of the building. I calculated the time and the velocity. Here it's kind of backwards. But it gets the same equations. Well, the first thing is I have to break down the velocity into its vertical and horizontal components. In this case, the velocity is a vector term. So I basically have a right triangle with an acute angle of 35 degrees. And the vertical component, which is a smaller value, is would be the vertical velocity, which would be given by 45 degrees. Sine of 35 degrees gives me 25.8 feet per second. So the building height I can get, the building height would be d naught like before. I know what the the vertical release velocity is. It's vertical upward. So my v naught is 25.8 feet per second. So I can solve this out. I write my distance equation. My d naught is what I want to solve for, the height of the building. I know that at some point it's going to whack into the ground, at which point d is equal to 0. And I know my initial velocity v naught is 25.8 feet per second. I know g, so I should be able to solve for t. No, I know t, it's 13.8 seconds. It was given. So what I could do is I can substitute in all those numbers and solve for d naught directly. And you see that how that goes there. I've substituted in all the numbers. You solve for d naught. Comes out to be 2,710 feet is the height of this building. I don't know if it's still the tallest building in the world. Certainly it's quite tall. It's 2,700. It's like crudely a half mile tall. It's a pretty tall building. Okay, this shows a plot of what the distance or height as a function of time would look at for my ball, or for Larry's ball, I should say. It turns out that you can't really tell, but right at the distance from the building, it's versus the distance away from the building. But basically, the ball is as it gets chunked, it actually has a very slight vertical component. So the maximum of the parabola is actually not at 0, but is actually out a little ways, maybe just maybe 10 or 20 feet from the building. But then we show it falling, and so it falls. One thing that we pick up here is we see that it goes to 0. It actually will hit the ground about 500 feet away from the building. It turns out that, and we can get the distance from the building. I can get by taking the horizontal velocity and simply multiplying it by the time. So the distance out would be 45 feet per second times the cosine of 35 degrees. That's the velocity, then times the time, 13.8 seconds. That gives me my horizontal distance. Okay, well, that leads us now to trajectories, which are basically what I just did, where I'm slinging an object in space in a gravitational field. And so I can show you here, we basically we could think that we could, basically the detail we need to know about firing the object is that there's a certain angle relative to the horizontal theta, and there's a certain v naught, the initial velocity. And again, this is the total initial velocity, not just the vertical component. So I have a V naught total velocity fired off at an angle of theta. And what happens is the object would fly like this. It flies up, it goes through a maximum and then lands on the earth, I guess, if we don't impede it otherwise, some distance away. So we have a curve that looks like this. Well, at any point on this curve, I could describe a horizontal distance, which is a function of time, and a vertical distance, which is a function of time. And so it turns out that we can get these two. I've actually, both of them we've discussed already. Let's do the horizontal first. The horizontal distance, again, as I mentioned, the horizontal component of the velocity is V naught cosine theta, as you see from the plot. And the object basically moves at a constant velocity. So there is no acceleration horizontally. It's simply scuttling along at that velocity until it hits the ground. So the horizontal distance is simply velocity times time. And so that would be V naught cosine theta times time. That gives me the time dependence of the horizontal distance. Now the vertical distance, again, as we've been talking about it follows the rules of acceleration because it's actually has a force imposed on it due to the gravitational field. So again, this would be by d naught, the vertical component. I use the subscript v. It's going to be d naught v, where I use the subscript to mean this. If this is d naught v is the initial distance vertically of the object, again, which is often taken to be 0. And I also have a vertical component of velocity at the start of the trajectory, which would be my v sub d naught in this case, times time plus 1/2 gt squared. So that's that part. Again, g is my acceleration due to gravity. I have that term given. So one of the things we can do is I can calculate the maximum distance that's the horizontal distance traveled. You can look at my little graphics, my dh max. The question, we can calculate that because I can notice that dh max is where the distance, the vertical distance, is equal to the initial vertical distance. Again, typically they're both equal to 0, but they don't have to be. They simply would be the same vertical height. And if that's the case, then looking at the equation for the vertical distance, that's immediately above there, the first term on the left side and the first term on the right side cancel each other. And so the second and third term on the right side of the equation have to be equal and opposite to each other. And I show that equation here. You solve for time. It turns out that the time that it takes for the object to come back to the same height where it started is minus 2 v naught sine theta over g. So effectively, we might call this the time of flight. It's the amount of time that the object is in the air, as it were. So that's one useful equation, the time of flight of an object. And we'll ask questions about that sometimes on the test. I can, since I know the time t is given, I can substitute that back into my horizontal distance equation, and that will give me dh max. So you see that again, I simply substitute that value of t, the time of flight, into the general horizontal distance equation. I do a little bit of math and reduce it down. It turns out that the horizontal maximum distance traveled is minus v naught squared sine 2 theta over g. Again, I have to use some trigonometric identities to get there. So that's the second equation that's kind of important when we're doing trajectories, is to know the maximum horizontal distance and the time of flight. Now, the next question that we can ask is, what's the vertical maximum distance, which you see here on this graphic, the maximum height above the starting point. And because the curve is parabolic, and we're, in this case, obviously, we're neglecting air resistance, which makes it parabolic. What we can do is we can get the vertical distances simply at a point of half the time of flight, right? So if I take the total time of flight divided by 2, that will be the value where I'll have my maximum vertical height. So again, I take half the maximum value, half of I take the time of flight divided by 2, you get the equation seen here. Then I substitute that into my dv equation. So I substitute time in at the 2 places here, like that, do a little math to cook it down. It turns out that the maximum vertical distance is my starting vertical distance minus v squared, v naught squared, sine squared theta over 2g. So that's the gives the equation for the maximum vertical height, which is the third equation in trajectory equations that we play around with. Okay, well, let's see. Let's work a couple of problems and I think we'll be done. Here's the first one. Kate tosses a ball off the building with an initial vertical velocity of 25 feet per second. If it hits the ground 3.4 seconds, how tall is the building? Well, this is a lot like the one we've worked before. In this case, I can work using the following equation. I substitute in, calculate the height. This again, it's very similar to the problem we worked with the Dubai building. And what I see is that the initial vertical distance is 101 feet, which would be the height of the building. Here's one more. This one maybe is a little bit more interesting. This came from 2012 on test F, which was the first district test. In Olympic archery, the archer shoots an arrow with an average speed of 320 feet per second, which is reasonable for Olympic archers, at a target 70 meters away, which is a standard distance for Olympic archery. So assuming the arrow is released at an elevation equivalent to the target's bullseye, which means that basically the arrow is going to travel, have a slight positive arc, and then come back to the same level, so that I can use my d horizontal max equation. Then, assuming that, it says, what should the archer's release angle be? Positive less than 45 degrees with 0 degrees parallel to the ground. The reason I have to talk about positive and less than 45 degrees will become apparent in a minute. It turns out that there actually are two different angles that the archer can use to shoot and hit that target at 320 feet per second, 70 meters away. So we'll see how that works. It'll fall out in the math. And then I'll talk about the physical significance of that. Okay, so I can, because the end point and the starting point are the same, I can use my DH max equation. This is, I wrote that here, just simply reproduced it. And I would set this equal to 70 meters. And so I can do that. I do some unit conversion on my 70 meters to come up with 230 feet. And then I substitute in my terms. I know the velocity V naught. I don't know theta. I know the acceleration G, and I know the distance DH max. And so I can solve this out for theta. So I get sine 2 theta equals 0.0723. Turns out, though, that there's a trig identity. Turns out that sine of 2 theta is equal to the sine of 180 degrees minus 2 theta. So basically, I have two different solutions for this. So looking at this, basically, when I take the inverse sine of 0.0723, I get 4.14 degrees. If I can set that equal to 2 thetas, so 1 theta is equal simply to 2.07. That's where I set it equal to 2 theta. But if I set it equal to 180 minus 2 theta, I get 87.9 degrees. It turns out that for most cases like this, what I can do is I can shoot. Basically, I can shoot very close to horizontal to get to the target, which would be the straight shot. I typically call that scudding. Or we could shoot it shoot the thing way high up in the air and have it come down almost vertically onto the target. And that's I call that typically a lob. So in that case, it would be 87.9 degrees. So in order to have a single answer, which is what we like on calculator problems, I have to say that we want it to be less than 45 degrees. And indeed, if you ever saw an archer at Olympic archery, they're shooting virtually level on the plane at the target, not shooting this big lob up into the air. So, but having said that, both of them work. So basically, if I have a horizontal distance I want to reach, there typically are two angles that I can use to get it for a given starting velocity. And those two angles are basically equidistant away from a 45-degree line. So if I shoot at 45 degrees, then there's only one angle, 45 degrees. But if I shoot at 5 degrees higher at 50 degrees, and it goes to a horizontal distance, I could also shoot 5 degrees less than 45 degrees or 40 degrees and hit the target or have the same horizontal maximum distance. So that is 40 degrees and 50 degrees will give me the same horizontal distance if I shoot the same velocity. Likewise, 20 degrees and 65 degrees, I guess, would 20 degrees would be 25 degrees less. So it'd be 65 degrees plus 25 degrees and 65 degrees would give me the same horizontal distance traveled if I shoot with the same velocity. So this is one thing you have to be kind of careful of is which theta when you're solving for the angle of departure, the exit angle for the object as it goes flying through the air. You may have, sometimes you have to be careful with these angles because there are two angles that will give you the same distance. Obviously, the maximum vertical height of the object as it trajects through the air is much different for a scud and a lob but the horizontal distance would be the same. Okay, I think so. I get in this case, obviously the answer, since I want it to be less than 45 degrees, my answer is 2.07 degrees. I think that takes me to the end of this. I hope that this was informative. Again, I would say in summary that what we're really looking for with trajectory problems is you have three equations, basically. You have a time of flight equation, you have a distance equation, you have a vertical distance and a horizontal distance equation, and then you have the velocity term that during that acceleration. So that's the case for trajectories. For acceleration deceleration problems, you have that only the acceleration equation for velocity. That velocity equals v naught t plus. I'm sorry. V naught t plus velocity equals acceleration times time plus v naught. And then you have the distance equation, d is equal to d naught plus v naught t plus 1/2 at squared for the distance. And then we have additionally, we can modify that for the trajectory equations as I mentioned. So anyway, so I hope that was useful. With that, let me go ahead and sign off.